Hi everyone, this is Gabriel Bathie from ENS Lyon, and today I'm going to present to you our work on property testing of regular languages and its application to streaming property testing of visibly pre-trained languages. This is joint work with Tatiana Starikovskaya from ENS Paris. So first, let me introduce you to property testing. Its study was initiated in the 90s, and basically the idea of property testing is to decide efficiently whether some object X has a property P or is epsilon far from satisfying it. Before explaining to you what epsilon far means, let me give you a few examples. So, for example, if X is a graph, and then P could be X is triangle free. If X is a Boolean function, P could be X is constant. If X is a word, P could be X belongs to L, where L is some language. And so here, epsilon is some positive real parameter. And so you have some notion of distance d, which depends on your application. And we then define the distance between x and the property p as the minimum over all y that have property p of dxy. And we say that x is epsilon far from this property p when this distance is greater than epsilon times n, where n is the length of x. And so in this setting, the algorithm has random access to the input x by queries, and the objective is to minimize the number of queries that the algorithm makes to the input. So in our work, we focus on the case where P is a property x belongs to L, where L is a regular language, that is a language defined by a regular expression here, or a finite automaton here. And more formally, if sigma is an alphabet and d the distance for words over sigma, then an epsilon property tester for the regular languages under the distance d is a randomized algorithm such that given a word of length n and a finite automaton a, this algorithm accepts with probability at least 2/3 words that belong to the language A, and then reject with probability at least 2/3 words that are epsilon far from this language. However, no answer is specified when the distance between u and L of A is between 0 and epsilon n. It could be 0 or 1 indifferently. And so, as I mentioned before, T has free access to u. And there is a particular case when when T always accepts inputs that are in A, and in that case we say that T has one-sided error. And so here the complexity measures are the usual time and space, and also queries, and we focus on minimizing the number of queries. And we measure them in terms of n, the length of the input, parameter epsilon, and m, which is the number of states of the automaton. So this problem was first studied by Alan et al. In 2001, and they showed that a surprising result. Actually, this is possible with a number of queries which does not depend on the length n of the input. It only depends on n and m and epsilon. And the number of queries that the algorithm makes is m cubed times 1 over epsilon times log 1 over epsilon to the 3. And the runtime of the algorithm is exponential in the size of the automaton. They also proved a 1 over epsilon lower bound on the number of queries that such an algorithm makes. And the algorithm works for the Hamming distance. And more recently, Ender et al. Improved that result by showing that it's actually possible to have an algorithm with a polynomial runtime. Also, François et al. Studied this problem, and even though their algorithm did not improve the previous one, they had a really interesting idea that they could use to improve the algorithm, but they didn't go that far. And so, what we do in our work is we improve the number of queries and the runtime to 1 over epsilon times log of 1 over epsilon. So we reduce the exponent from 3 to 1 on the log. And we also show a matching lower bound of 1 over epsilon times log of 1 over epsilon queries. And our algorithm works for the weighted edit distance because we will need this distance in our application later for visibly pre-trained languages. And so our analysis basically combines the ideas of these works, and we also add a layer of a tighter analysis on top of all this. And for the lower bound, we use Yao's min-max principle. I will give you more details later. And so, as I said, we apply this result on regular languages to another class of languages called the visibly pushdown languages, which were introduced in 2004 in the context of formal verification and program analysis. So visibly pushdown languages, or VPL for short, are languages recognized by visibly pushdown automata, which are just restricted pushdown automata in the following sense: the action that they take on the stack only depends on the letters that they read, not on their internal state. This means that for some letters, you will always push a symbol into the stack, and for some letters, you will always pop a letter from the stack. This makes sense in program analysis because some letters will correspond to function calls, and some letters will correspond to return from the function. Or more simply, you can see pop letters as opening parentheses of one kind and pop letters as closing parentheses of another kind. And it was shown that VPLs are hard to recognize in the following sense: they require at least n to the 1/5 queries to be recognized in property testing, and they require linear memory to be recognized in streaming. So there was a question of whether can we get to something which is porting email into login. And so the answer is yes in the following sense. If we change models and we look at the streaming property testing model, which is a combination of the property testing and the streaming models, in the following sense. So a streaming property tester for visibly pushdown languages is a randomized streaming algorithm. So it means that it has sequential access to its input, but once it reads a letter, it cannot go back to read the letters before. And on top of that, we add the property testing relaxation, which is the algorithm must accept with good probability inputs that are in the language. It must reject with good probability inputs that are far from the language, but it can answer anything for words that are in between. And so here's the complexity measures are time used per letter and the space used, and here we focus on reducing the space that our algorithm uses. So this model was introduced. This problem was studied by François et al. In 2015, and the design the streaming property tester algorithm that uses space 1/epsilon to the 4 times log n to the 6, and we use our result for regular languages to improve this algorithm to 1/epsilon to the 3 times log n to the 5 log n space. So now I'm going to go back to the regular languages and give you more detail about our result, which is the following. There exists a property tester for regular languages under the weighted edit distance that makes 1/epsilon times log of 1/epsilon queries and has one-sided error. And we also prove a matching lower bounds for non-adaptive one-sided testers. I'm going to give you the proof in the case of the usual edit distance, not weighted, and I will let G denote this distance. And in what follows, A is a finite automaton and L is a language that it recognizes. So the key idea behind these algorithms that recognize regular languages with a constant number of queries is the idea of A blocking word. A word V is A blocking if it is not a factor of any word of head of A. In other words, V only labels invalid runs in A. So let me give you an example. Here, L is a language of words that are 0, 1, 0, 1, etc. And so let's look at the word V equals 1, 1. Wherever we start in this automaton, we always end up in an invalid state. So if we start here, there is no transition labeled by 1, so it's already invalid. And if we start here, first we use the first one to take this transition, and then we are stuck because there's no transition labeled by 1. So the idea of the algorithm is just to try to find a blocking factor in the word. If we don't find one, we just say, well, the word is in the language, and if we find one, we know it's not in the language. And so notice that we only have to find one when the word is epsilon far from the language. And so we can actually prove that when the word is epsilon far from the language, then it contains at least C epsilon and disjoint A blocking factors of length which is bounded by C over epsilon. And this is sufficient to obtain a tester that makes one over epsilon request queries. This is basically the tester of François et al. So now I will tell you how we do to go a bit further below this one over epsilon request queries. The idea is to analyze on a low level the size of the blocking factors. What we do is we partition the blocking factors according to the sizes into buckets, and so the bucket ST is going to contain the blocking factors that have size between 2 to the t minus 1 and 2 to the t minus 1. So instead of partitioning them linearly, we partition them logarithmically. And so here t goes up to logarithm of the maximum size, which is on the order of log of 1 over epsilon. And then, by the pigeonhole principle, there must exist a t0 such that the bucket st0 contains at least epsilon n over log of 1 over epsilon blocking factors of this size. And so we now focus on this bucket. We ignore the other buckets. And what we do is we sample a random factor of length twice the length of the longest factor in st0. And we look at the probability that when we do this, it contains a factor from st0. So first thing that we can notice is that each blocking factor of st0 is contained in at least 2 to the t0 such factors w. Like we have enough room to slide w in 2 to the t0 and it still contains v. And conversely, each w contains at most 4v because v has size 2 to the t0 minus 1. So there's at most, and they are disjoint. So there can be at most 4 of them. This means that the probability that this w contains a v is at least 2 to the t0 minus 2 times the size of t0 divided by n, since there are n positions in the word. And by plugging in the size of t0 here, we get that this is at least 2 to the t0 times c epsilon over log of 1 over epsilon. And so if we repeat this process on the order of the inverse of this number times, we find one with constant probability. So what's the cost here? We have to pay 2 to the t0 plus 1 queries for one factor, and we repeat that many times. And so this multiplies up to 1 over epsilon times log of 1 over epsilon queries. However, there is an issue here. We don't know the value of t0 for which the bucket contains sufficiently many blocking factors. So we have to try all values of t0. Thankfully, there are only a logarithmic number of them, so that gives 1 over epsilon times log of 1 over epsilon queries. There's another issue though, which is that at some point during the proof, we have to go from automata that have one strongly connected component to automata that have multiple strongly connected components. And so this costs a factor of log of 1 over epsilon. So in total, we get 1 over epsilon times log of 1 over epsilon to the 3. And this is basically the tester of Alan and Indian et al. And this is where François et al. Come in, because in their work, they have an idea which allows them to construct a decomposition of U, which allows us to remove that log of 1 over epsilon factor. They don't use it in their work, but if they did, we could get 1 over epsilon times log of 1 over epsilon squared. And so I will now show you how we did to go one step further and get the log to the power of 1. We can notice that in the previous analysis, we only computed the probability that the queries that we made for some t find a factor that is in st. But actually, it's possible that the queries for some t find a factor that belongs to a bucket st prime for some smaller t prime. But then the probability is smaller. And so if we do an analysis that takes this into account, all things cancel out nicely, and we find that 1 over epsilon queries per bucket are sufficient. So by using the idea of François et al. As well, we get a total of 1 over epsilon times log of 1 over epsilon queries. And this is how our tester works. Right, so now I'm going to give you details about the proof of our lower bound, which is following. Any non-adaptive property tester for regular languages with one-sided error uses at least 1 over epsilon times log of 1 over epsilon queries. Here, non-adaptive means the position of a query cannot depend on the results of previous queries. So basically, you send all of the queries, then you get all of the results, then you decide. So in order to prove this lower bound, we use the famous Yao min-max principle, which says that basically if there exists a distribution U of inputs that is hard for deterministic testers that make at most 2 queries, then any randomized tester that uses at most 2 queries must fail on some input U. And when you state it mathematically, it gives the following equation. So this means that we just have to find distribution U, that is that any deterministic algorithm that uses less than C times 1 over epsilon times log of 1 over epsilon queries failed with constant probability. I am now going to describe how we build such a distribution. So the first idea was that the language parity is hard for property testing. So parity is a language of words that have an even number of A. So it's hard because basically, even if you read all letters but 1, there's still a possibility that the number of A is even or odd. So you need a linear number of queries. But you can notice that this is not really useful here because the distance between a word and parity is always 0 or 1, because by changing one letter, you can always change the parity of the number of A. So no input can be epsilon far from the language. So what we did is that we created another language which basically considers words that encode multiple instances of parity, and our language only contains the words for which all instances are positive. And also, to obtain a hard instance, we had to ensure that every bucket ST that I mentioned earlier is equally full. That is, they all contain 1 over epsilon log of 1 over epsilon negative instances, because otherwise there is an algorithm that can solve the problem. It is an algorithm that basically guesses the correct bucket. And also, if you remember what I mentioned before about this word W that slides over the blocking factors, the worst case is basically when all the blocking factors of the same bucket are next to each other. So we just build a distribution that corresponds to this, and it turns out, after a bit of computation, that it is indeed hard for any property tester that makes less than the number of queries that we showed. And that's how we get our lower bound. So finally, I'm going to give you more details about our results on visibly pushdown languages, which are the following. First, there exists an epsilon streaming property tester, or SPT for short, for VPLs under the edit distance that use space epsilon to the -3 log n to the 5 log n and that have one-sided error. And we proved a lower bound on the space that might be used to recognize VPL in this model of log n plus 1 over epsilon. And in what follows, G is the edit distance, A is the visibly pushdown automaton, and L is the language that it recognizes. For the upper bound, we use the work of François et al., which basically showed that epsilon streaming property testing of visibly pushdown languages under the edit distance can be reduced to many instances of epsilon prime property testing of regular languages with the following constraint. It has to be under the weighted edit distance. The instances have linear size. Epsilon prime is equal to epsilon over log n. Each query becomes 1 over epsilon space, and you have to reduce the error probability from 1 full to 1 over n. So you have to take log n copies of all of your instances. And so when you add up all of this and plug in our tester for regular languages, you actually get an epsilon SPT that uses space epsilon to the minus 3 log n to the 5 log n bits of space. So this is a straightforward application of the construction of consortia. Now I'm going to give you more details about our lower bound, which is not a straightforward application of our previous lower bound. So in order to prove this lower bound, we first prove a lower bound for deterministic SPT, which we then generalize to randomized SPT. So a deterministic SPT is a streaming algorithm that must accept words that are in the language, reject those that are hard, and is not constrained on the other inputs. And so the theorem that we can show is the following. Any deterministic SPT for the language of palindromes must use linear space. And we can then extend this result to show a logarithmic lower bound for randomized SPTs. So the idea of the proof is the following. We look at the memory state of the algorithm after it reads the first half of the word. So let's consider two half words U and V. And so we can prove that if the distance between U and V is sufficiently large, then the distance between U and V in reverse is epsilon far from the language of palindromes. And moreover, if the algorithm is in the same memory state after reading U or reading V, then it must return the same result on U reverse and V U reverse, because it cannot distinguish whether it had read V or U. So in order to satisfy the definition of an epsilon Turing property tester, it means that two half words that are mapped to the same memory state must belong to the same ball for the exit distance of radius 2 epsilon n. And we can also show that we need an exponential number of balls of radius 2 epsilon n to cover the set of all half words. This means that the algorithm must have an exponential number of memory states, and this requires linear memory to encode them. This means that any deterministic Turing property tester for this language must use a linear amount of space. And so in order to generalize this result to randomized Turing property testers, we use probabilistic automata. The idea is the following. We can see a streaming algorithm restricted to inputs of fixed length as an automaton, and when the algorithm is randomized, the automaton is probabilistic. The content of the memory corresponds to the state of the automaton, and when the algorithm reads the data, it changes its memory states, and it means that the automaton makes a transition. And we then use a result by Rabin, which says that for every probabilistic automata with S states, there exists an equivalent deterministic automaton with at most 2 to the S states. And so we can use the converse of this result, which means that if we have a linear lower bound on the number of states or on the space of an SPT, then we have a logarithmic lower bound on the number of states of the memory used by a randomized SPT. So that's how we generalized our lower bound to randomized SPTs. Alright, so yes, as I said, that's how we generate the lower bound. Alright, so here's a summary of our results, and before concluding, I'd like to make the following remark, which is that I believe that our lower bound for the property testing of regular languages can be adapted to work for algorithms with two-sided error, which means that the only condition left on our lower bound would be that the algorithm is non-adaptive. And so this seems to ask whether adaptivity can help here. So the question would be either to prove that the lower bound also holds for non-adaptive algorithms, or to actually find an adaptive algorithm that solves the problem with fewer queries, for example, one or epsilon queries. So I think that's a non-trivial and really interesting question. And on the other hand, the question is kind of the same for visibly pushdown languages, I find it hard to believe that this upper bound is optimal, so the question would be, can we improve this upper bound? And maybe the lower bound can also be improved. I believe the optimal should be more something like log n to the something divided by epsilon. So that's the other question. All right, thank you for listening. If you have any question, feel free to send me an email or to come to the conference at iHelp, and see you there. Bye.